A current can create a magnetic field, as we've seen, so it's natural to wonder if it works the other way. Can a magnetic field create a current? No. Ish. Experiments by Michael Faraday and others indicated that while a steady magnetic field doesn't create a current, a changing one can. He actually investigated several different configurations. In one case, he had two circuits that were not connected, but they each had a coil of wire in them, and one was hooked up to a galvanometer, which is a thing that measures current basically, and when there's current flowing, the needle deflects. And he found that when he closed the switch, the needle would pop over and deflect momentarily, but then go back to zero. And then when he opened the switch, which of course erases this current and therefore erases the magnetic field, it would spike again and go back to zero. So it was the creation of the magnetic field by putting current through it that seemed to create the current, but only momentarily. Then he took a similar circuit that had a coil in it hooked up to a galvanometer and pushed a magnet through, and found again that when the magnet was passing through the loops that there would be a spike of current, but when the magnet was removed, there'd be a spike of current again. But if the magnet were simply held inside the circuit loop, inside the coiled wire, then there would be no current. So it was only as the magnet was moving through the coils that you got current. And then he did something similar. He took a C-shaped magnet with a relatively strong magnetic field going this way, going like that, and found that when he pushed a circuit with a coil in it through and into this magnetic field, he got a current spike. In fact, what he found is that you got a spike in any of these cases when you opened or closed the switch, or pushed or pulled the magnet through the coil, or moved the coil through a magnetic field. What seems to matter is that the magnetic field that's passing through the coil of interest is changing. So in the first case, of course, we have magnetic field coming, say, like this, which I guess we should figure out means that the current is moving the current is moving that way around the coils. And as we move closer in, as we bring this, as this current grows, because we've just closed the switch, that field gets more and more intense, and so grows in this region. Or if we move a permanent magnet through the coil, out here, when the magnet's back here, there's very little field through the coil, but as we come in, we get more and more field passing through this region of space. Or in this case, the magnetic field is constant, but I move the coil in, and again, the amount that's going through the loops is increasing. And it seems to be that that's what matters. This type of current is called induced current, and the phenomenon is called electromagnetic induction. You've noticed we've used this word a lot. To induce something is when there's a response, but only while we're doing something that causes that response. There's no permanent response, but just in the presence of, for instance, induced charge polarity, when we bring a charge near an insulator and we realign the electrons and protons, but only temporarily, and then when we take away our charge, their polarity goes back to zero. We've seen that for a bunch of things that where we say we're inducing things. Here we're inducing current by using a changing magnetic field. Of course, that induced current would be driven by some EMF, but it's not the type of EMF we've been studying. It is, as you might expect, called induced EMF, also called motional EMF. And you might wonder legitimately, where is it coming from? Is this some new magic phenomenon we have to talk about? And the answer is, actually, it's not entirely a new thing. Let's consider a conducting rod being dragged through a magnetic field as shown. We'll assume the magnetic field itself is external and constant. If we are pulling this way through a field going into the board, the right-hand rule says that there is a force on any given, say, positive charge in the rod that will tend to move it upward. It's moving over, but it also feels an upward force, and so the positive charges will flow to the top of the rod. And exactly the same analysis, but flipping the sign, means that the negative charges will flow to the bottom of the rod. Now we've gathered charges on both sides of the rod, so there is some sort of potential across the rod. As we keep moving this, more and more charge will move up until at some point there is an electric force opposing the motion that equals the magnetic force that's trying to move it upward. This is coming from the potential, which remember drops from here to here, so there's an electric force on positive charges that would be downward. All right, and so we have created a voltage difference in EMF across these rods, across these ends of these rods. As the charge builds up on the ends of the conductor, the imbalance creates an electric field that opposes further motion, and eventually that force equals the magnetic force, and no more charge flows because the forces are equal. Here we should say no more flows up or down. It's still moving over because we're dragging the rod over. The electric force, of course, is Q times the electric field. The magnetic force is Q times velocity times the magnetic field. And the electric field itself is going to be, I guess first thing we'll do is cancel, right? We can cancel the Q's. And we have E equals VB. But the electric field itself is delta V over the length of the conductor. So we get, at the end, we get that delta V, the potential difference is Q times L times B. Typographical thing, and I wouldn't have chosen this, but your textbook does. That's an L, not an I. Just be careful as you read these things. Lots of I's floating around too. All right, we're going to derive a word, and we're going to say that batteries generate what we now call chemical EMF because of the chemical reactions inside the battery that's providing the energy and doing the work. Moving conductors generate what we call motional EMF because it's the motion that's causing work to be done on the charges. Now, an EMF existing by itself isn't all that interesting, but if we hook up a conducting path, we create, for instance, a wire that loops these two things together. Now there's a path for these positives. There's new positives coming up, remember. These positives can flow, and so they'll flow down here, and we'll get a current, what we've called an induced current. The setup here is, imagine we have two long rails that are fixed in place. They're held by something else. And then we've got a length of wire or conducting rod or something that's free to move, and that there's good contact between the two. The wire will have some, I'll assume we'll just use this conducting rod will have some resistance. And once we've created this EMF, there is essentially a pressure here that allows the positives to flow around. And so we get a current which is counterclockwise, and we can figure out how large it is because the current, of course, is the EMF produced over the resistance, right? Standard circuit analysis. And the EMF was VLB. So the current produced is VLB over R. Is this a thing you should memorize? I don't think so. I think it's pretty quick to rebuild from the fundamentals. But if you feel more comfortable memorizing it, I guess it's not a bad one to know. Of course, now that there's a current in the rod, it will interact with the magnetic field as well. Right? You should be able to convince yourself pretty easily that this field produces a force that points leftward, because now we'll take right-hand rule. We have I going that way. This is our out of the board direction. So the magnetic field is into the board, and the curl of those things gives you leftward. Hey, notice that opposes the way the rod is moving. It's like a resistive force, a frictional force, or at least, as we like to call it, a drag force. It's what's called magnetic drag, which if we were to let go of the rod, we would very slowly, or maybe very quickly, but we would reduce the speed of the rod, which would reduce the current. So we have this weird drag force, but it's not a constant drag force. It's actually very close to a resistance type force. And it would slow the rod down until eventually the rod would stop. Unless, of course, we exert a force that keep it moving. All right? It's the work done by our external force that keeps the rod moving at constant speed that puts energy into the circuit. That's what's doing the work that turns into the energy inside the circuit. All right, we can compute the force needed to keep the rod moving at constant speed relatively easily. We know that the pull that we have to exert equals the magnetic force that's being pulled backward. But the magnetic force, of course, is going to be I times L times B. But we also know that I, we just found, was VLB times L times B. Over R. There's an over R here. And so we end up at the end with VL squared B squared over R. So a couple of things. The drag force is proportional to the velocity, which means that it will look a lot like air resistance, which is also proportional to velocity. So there'll be, well, I guess here, no terminal speed necessarily, but instead it will head towards 0, and it will do so exponentially. And the acceleration will be also exponential. Also, it's inversely proportional to the resistance. So if we can lower the resistance somehow, we can make the drag force larger. This is because, again, we're setting up currents in the conductor. We'll generally call these things eddy currents because they tend to swirl around the conductor. So consider this. The 3 rods here are non-magnetic but conductive. There are 3 powerful ring magnets, one surrounding each rod. So you can see them, although they're a little hard to tell. They're relatively powerful neodymium magnets down here. And the question is, if the 3 rods are raised to the top, the 3 rings are raised to the top and let go at the same time, which one reaches the bottom first? The copper, the aluminum, or the brass? And it's probably worth knowing, if you don't offhand, that these are in conductance conductivity order, that this is very conductive, this is a little less conductive, this is least conductive. All right, let's walk through and see.
In this demonstration, I have 3 metal rods, a brass rod, an aluminum rod, and a copper rod. I also have 3 strong ring magnets, which can move freely along the rods. Now, each rod is not magnetic in any way. So what I'm going to do is I'm going to bring all 3 magnets up to the top and let them go at the same time. The question is, which magnet will reach the bottom first? Will the magnet on the brass rod reach the bottom first, on the aluminum rod, the copper rod, or will they all reach the bottom at the same time? So as you can see, the magnet on the brass rod made it to the bottom first, and then the aluminum rod, and lastly the copper rod. This is due to eddy currents being set up in each rod by the magnet, and eddy currents also depend on the conductivity of the rod. Copper has the highest conductivity of the 3 metals. Next comes aluminum, and finally brass. So that was the order in which the magnets finished: brass, aluminum, and copper.
All right, to recap for just a second, the drag force is inversely proportional to the resistance, which means it's proportional to conductivity. Copper had the greatest conductivity, so it had the highest drag force, so it moves the slower, it reaches its terminal speed faster. Why is there terminal speed here? Because there's also gravity pulling down just when we drop something with air resistance. And so it gets to a lower terminal speed and gets there faster. And so on average, it's moving less quickly. There's a little bit of a cheat here, which you might have noticed, which is that we talked about moving a rod through a constant magnetic field. Here, the rods are stationary, and it's the magnetic field that the magnet that's moving, and is that still legit? And the question is good to ask. It turns out it is still legit. As we know in physics, generally you can switch to the other frame of reference. But we do have to be careful with magnetism when we do that, because magnetic effects are sort of tied into things like special relativity. So switching reference frames can be a little risky, although it works here, where we can pretend instead of the magnet falling down the rod, that the rod is being pulled up through the magnet, and it works the right way, although if we tried to calculate it with our expressions, we would get something not quite right.